Among the different types of noise, the first noise what we are going to see is thermal noise. So you know thermal relates to temperature. So this noise has a strong dependence on temperature. And thermal noise was found by Johnson. So he first made an experiment to measure the thermal noise in resistors, and Nyquist, along with the help of Johnson, they completely modeled the thermal noise. The thermal noise is predominantly found in resistors. You know, resistors have lot of electrons inside, and even without any current is flowing through the resistor, these electrons flow randomly inside the resistors. So what is called as Brownian motion. So Brownian motion is a random movement of electrons which will create some sort of random current or voltage. So when these random charge carriers will move inside the conductor, which gives rise to a current, which gives rise to a random voltage. You know, by Ohm's law, V is equal to IR. So as the current is produced through, as the noise current is flowing through the resistance, by Ohm's law, we have V is equal to IR. So you have a random voltage which is developed in the noisy resistor. So thermal noise is predominantly found only in resistors and not in other components. And if you are going to use a resistor inside an amplifier, that amplifier will be affected by thermal noise. Okay, the thermal noise is also called as Johnson noise or Nyquist noise because of the massive contribution by these two people. And but we use the former name. You mostly refer thermal noise with Johnson noise, and we don't refer it to as Nyquist noise. Okay, so mostly it is called as a Johnson noise. One important characteristics of noise is you cannot have a clear-cut mathematical equation for noise. If I say x is equal to sine omega t, so you can write this equation. I can plot this equation in a graph, and I can have a tabular column having the values. By varying omega and t, I can plot this graph beautifully. But this noise is going to be completely random. Random in the sense, at every instant of time, the value possessed by this noise is going to change. It is not going to be same. So you cannot identify a specific voltage at a particular time. So whenever something is random, we always go for probability theory. So definitely this noise is modeled by probability theory, and we assume the most familiar noise model, what you know, is Gaussian distribution. So we model this thermal noise using Gaussian distribution. So you know Gaussian distribution is a bell-shaped curve. So the bell-shaped curve will have values. So this is the graph of a Gaussian distribution. It is a bell-shaped curve, and this covers all values from 0 to 1. So it is probability. So definitely you cannot fix one value for noise. It will take multiple, can take multiple values at different points of time. The same noise, if you measure today at 6 o'clock, it will be say 5 microvolt. The same noise, if you measure tomorrow at 6 o'clock, it will be 10 microvolt. So if you constantly measure for 1 month, you take the average, that is going to be the average value of noise. So remember, noise cannot be written by a single mathematical equation. We can only write what is the average value. So that average value, statistics, everything, probability, everything will come into picture when you are going to model noise mathematically. Okay. So remember, there is no single equation for noise. If you write a single equation for noise, it will definitely have the term having average value, because there is no instantaneous value in noise, because the instantaneous value is going to change every second for noise.